Hello, before starting I want to thank you for being present at this online event of the 18th International Renewable and Sustainable Energy Conference. My name is Hind, I'm a PhD student with joint supervision between Nantes University and Ftouhi University. In this presentation I'm going to talk about the enhancement of inverted planar heterojunction solar cell performances using cathode buffer layer. My presentation begins with an introduction, then the generality on the organic solar cells. The third point is about our work on the effect of KELQ3 as cathode buffer layer on the inverted organic solar cells. Then I will finish by a conclusion and perspective of our work. Organic solar cells have attracted a significant amount of attention due to the need to develop an inexpensive, clean, and sustainable renewable energy source. Briefly, the mechanism of these cells involves the following four steps. The first one is the absorption of the light, the diffusion of the excitons, and the next is the dissociation of these excitons. The final step is the transport and the collection of the charge by their corresponding electrodes. So for a better charge collection at the interface, a buffer layers are necessary to create or to get a good ohmic contact between electrode and the photoactive layer. Here we have the classical planar heterojunction solar cells. This type of cells consists of two organic semiconductors stacked between two electrodes, one with high work function as the indium thin oxide and another is the aluminum with low work function. The LQ3 thin layer with wide band gap was used as cathode buffer layer, and this thin layer can effectively block excitons and transport the electron from the acceptor materials to the cathode, as simplified here in this energy level diagrams. So during the deposition process of the cathode or the aluminum, the diffusion of in this thin layers facilitate the electron transport from the acceptor materials to the cathode. So when we use the inverted configuration where the indium thin oxide is the cathode and the aluminum is the anode, so contrary to the classical configuration at acceptor electrode interface where no metal diffusion can occur to facilitate the electron transport property. For that reason, and in that case, our goal is being to improve the electron transport at the electrode acceptor material interfaces by using KELQ3 double layer as cathode buffer layer. For the experimental work, the inverted organic solar cell was deposited by evaporation under vacuum with a pressure of 10⁻⁶ millibar. All the layers were deposited successfully, and the thickness of each layer was controlled with quartz monitor. After the thickness optimization, here we have the results obtained with our cell using KELQ3 double layer. So as you can see here in this table, the cell with 0.8 nanometer of Ke exhibits a better performances than the reference cells in terms of efficiency and the open circuit voltage. This last parameters was improved by 35%. This improvement made due to the band alignment between indium thin oxide and Louarn. So in order to understand the origin of this improvement, we analyzed the KELQ3 interface using X-ray photoelectron spectroscopy. In the XPX spectra here of the KELQ3 appeared two peaks corresponding to potassium 2P. The presence of the potassium on the interface indicates that is diffusion in the LQ3 thin layer. This diffusion may create a gap state to get a better alignment and therefore better electron extraction from the acceptor material. As a conclusion, the inverted organic solar cell with KELQ3 double layer has an efficiency improvement of 10% and open circuit voltage of 35% compared to the reference cell. Thank you for your attention.